In the previous lesson, we created a hello world style application, and then we issued the command .NET run in order to execute the application to get the output hello .NET Core. And I was, if you recall, very deliberate about checking and rechecking the files inside of the project directory. So I would constantly do dirs, or I would change into a given directory and look at the files that were outputted, because I wanted to understand what the commands that we've issued, the .NET driver commands, were actually doing for us. And in this lesson, what I want to do is kind of continue to understand better what's going on with the Core CLR, what it does, how it works behind the scenes, and so on. So I want to answer two primary questions. The first question is, what are its responsibilities? And then secondly, how does the Core CLR work internally, at least to the extent that we can see what's going on under the hood from an outsider's perspective. So let's start with the Core CLR's responsibilities. There are two primary responsibilities. The first responsibility is actually to be an application host. We'll talk about that more in a moment. And then secondly, if the application has not already been compiled into a machine language specific for the given platform it's running on, then the Core CLR needs to kick off that process too. So those are the two responsibilities. Let's start by talking about the first responsibility, to provide an application host environment which manages the execution of your application. So it will do things for you like will manage memory. We'll put things into memory, recall them from memory, especially objects. You know, you got the heap and the stack and all that good stuff. And so in order to perform this role, there's actually this baseline type system that include things like system.object and int32 and string and so on. Of course, it knows how to load assemblies. So if you have a library, a DLL, it knows how to load that and be able to execute code inside of it. We've already talked about the memory management, the garbage collection. It also knows how to do native interop. So if there are COM components that you need to call that are native, are non.NET native COM components, it'll know how to call them as well. And it'll also perform other basic services. That's what we mean by this application environment. It's actually been compared to like a virtual machine that your application lives inside of as it runs. It's a protective bubble for both the owner of the system and then the developer as well, to kind of add a layer of protection between them. All right, so that was the first responsibility, is to be an application host. But if the application has not yet been compiled into machine language, because the distributed assemblies have only been compiled into intermediate language when we run them locally, or even distribute them from the developer computer or the build computer to the actual target computer, then the Core CLR will actually kick off that process of just-in-time compilation. So you can see that there are equivalents between what's going on in the Core the .NET Core and the full .NET framework. They're almost identical in purpose and utility to the original .NET framework common language runtime. It does almost the exact same thing. Let's talk about execution for a moment. Core CLR execution. There's actually this fantastic article that was written by a guy named Matt Warren. So you can go to mattwarren.org and look through his blog posts. And you want to look for the one on July 4th, 2016, how the .NET CLI tooling runs your code. And this is pretty interesting stuff. He goes under the covers a little bit and kind of talks about what's happening and how it's happening. And it gives you some jumping off points as well. And so I recommend that you read this article after you finish watching this video. I'll remind you at the very end. So keep watching this for now. But in a nutshell, he flipped on a few environment variables inside of his copy of Windows. And then what it did was it enabled a more verbose mode that developers use for debugging purposes. Whenever his application was then compiled and run, he was able to see what was going on whenever running these .NET New, .NET Restore, those sorts of things. All right, so he's got some insights with that. I'm going to talk about just-in-time compilation in just a moment, so we'll ignore that for now. But essentially, he talks about what happens during that JIT JIT step, JIT, just-in-time compilation step. And the article discusses the process of execution, the different subsystems that are loaded, the process of finding all the necessary dependencies that your application relies on, and then loading them into memory. And then finally, after a bunch of prep work has been done, then your application is loaded and executed. So the main entry point for the application is located inside of your DLL, and the thread of execution begins to execute the commands inside of your main entry point. So again, this is a very low-level look into how your application is loaded and managed, and you won't need to memorize any of these details. It's just nice to kind of have and understand the overall process that's required for your application to actually work, especially across platform. All right, so that is basically execution. Let's talk about just-in-time compilation for a moment. So we said that the additional step that might be taken if your application hasn't been executed on a given platform is that it will be compiled from the intermediate language down into machine language. And so this optional step is called just-in-time compilation. You might see the term JIT, J-I-T, or jitter. This is a reference to a portion of the CLR that performs the JIT function. So C# and all the other programming languages that are utilized by .NET Framework and the .NET Core are designed to be human readable and understandable. Otherwise, even the simplest computer instruction that we were to try to write would be laborious for humans to understand and then to actually write or debug. However, the source code that human programmers However, the source code that human programmers write must be rewritten in a format that the computer and its operating system can understand before it can be executed on that computer. And so this process of rewriting the code is called compilation. Now, to further complicate the matter, each operating system and computer hardware architecture speaks a slightly different language. So here again, it would be laborious to expect programmers who are composing the higher level business functionality to understand each of the nuances of the language spoken by every operating system and all the hardware architectures that are out there in the world. So fortunately, compilers can do this for us very easily. That's a good task for them. So to support multiple operating systems and hardware architectures, the .NET Core compilers for each supported programming language, which in version 1 is only C#, but then we're also going to see VB and F# in upcoming versions of the .NET Core. They will compile our C# or VB or F#. It'll take the source language, C#, and compile it into something called intermediate language, or IL. So there's a specification called the Common Language Specification. Let's see if we can find it here. Look at Wikipedia, search for Common Language Specification. It'll explain a little bit about what it does. It defines the format of intermediate language so that compilers for new programming languages can also be compiled into IL. And we saw this in the original .NET Framework, where Python and Ruby were able to be compiled down into intermediate language as well. So this shared language integration and runtime platform allows different programmers to use their favorite programming language, but allow components that are written in all these different languages to actually speak to each other, because they all get compiled down to the same baseline intermediate language. All right. So compiling it first into intermediate language actually has another advantage. The burden of compilation can be delayed until the compiled assembly is executed for the very first time on a computer system. And so this makes it easy to distribute one assembly to avoid the confusion for the end user of which version of the assembly do I need to download for my operating system and my hardware. So you can see here, when we ran just a moment ago, we called the .NET Run function. It took a look and said it was previously compiled, so it's skipping compilation. But that's going to be one of the steps. Again, one of the responsibilities of the .NET Core is to see if there is a compiled version. If not, then to go ahead and compile it. And it will do that on the target computer, not on the development or the build server. All right. So when the user attempts to run the application for the very first time, the Core CLR, in this case, since we're talking about .NET Core, it'll see that there's no compiled version of the assembly, and it'll kick off that process of compilation into native code. Now, if we were to make a change to our code in the program.cs, and let's just do that real quick here, just to show what happens. So I'm going to go notepad program.cs, and I'll just add a couple more exclamation marks. It could be very simple. Let's just go ahead and do that, and then quit. And then let's go ahead and go .NET run. And you can see that just by virtue of the fact that we made a change, even a tiny change in our source code, it says that it'll be compiled because the inputs were modified. So compiling Hello World for the .NET Core app, that's the target, version 1.0, compilation succeeded with 0 warnings and 0 errors, and then it took a little over a second, and then it actually executed our new version of our application, now with 3 exclamation marks. All right, so you can see how that the just-in-time compilation happened. It did it so that it could compile my code into native code, or rather machine-specific code for my computer, for an end user's operating system and hardware architecture. However, it is possible for developers to pre-compile assemblies for specific operating systems and hardware architectures. Now, I'm not going to be covering that in any depth in this course. However, you can take a look at the phrase that you want to look for is native image integration. Native image generation. You can look here, or you can just search for this term cross-gen, which is a utility that's available in the .NET Core SDK for more information about that. But typically what you'll want to do is just allow the target computers to do the compilation on their own. Otherwise, it's quite a hassle. All right, so let's talk about the internals of the Core CLR for a moment. I'm always curious about how something like cross-platform actually works. So I asked myself, how is the Core CLR architected in such a way that it's able to function across multiple operating systems and system architectures? Well, I have no special knowledge of how this works outside of hints that I can glean by reading the documentation. So here's a particularly interesting passage from this .NET Core. You can find it here, this URL on screen. In this particular article, if you read the whole thing, it gets particularly interesting when you get down to this part called architecture. All right, so I plucked a few quotes from this. You might want to read the whole article after the video, but I want to call your attention to a couple of quotes. First one is, people commonly ask how the .NET Core is implemented in order to support multiple operating systems. They typically ask if there are separate implementations or if conditional compilation is being used inside of the .NET Core, my words. It's both, with a strong bias towards conditional compilation. So you can see in the chart below, here in this chart that they're referring to on screen right now, that the vast majority of Core FX is platform neutral code. So remember, Core FX is the actual library, not the runtime. But the Core FX library is platform neutral, that's shared across all platforms, and that's in the green color. Platform neutral code can be implemented as a single portable assembly that can be used on all platforms. Why? Because it doesn't rely on any special types or any specific functionality of any given operating system. But then later on, it'll say there are a mix of platform-specific and platform-neutral libraries in the .NET Core. You can see the pattern in a few examples. The Core CLR is platform-specific. It's built in C and C++, and so is platform-specific by construction. In other words, every operating system and hardware architecture has its own platform-specific version of the Core CLR. So there's a bunch of different Core CLRs that are out there, one for every platform that are supported in version 1.0. So things like system.io and then system.security.cryptography.algorithms, all right, they are also platform-specific because storing stuff onto a computer and then cryptography APIs for a given operating system are considerably different depending on every operating system. So here, if the .NET Core relies on an API provided by the operating system, then it's going to be, again, platform-specific implementations of things in the Core FX, like System.io, which deals with saving and reading stuff from disk, and then also cryptography algorithms, things that, again, are dealing with cryptography of information, like working with security certificates or encrypted conversations between two participants, things like that. But if we were to move up a level and look at things like system.collections and system.link, those are platform neutral. So we're back in the green code now in this diagram because they operate over data structures that are .NET specific. And so here again, take a look at this article. It's a great article. I learned a lot from it. And in particular, you want to, for this particular topic, we want to look at the section called architecture. So as I understand it, just to kind of recap what I just said here, the Core CLR is platform specific. And if we were to look at the Core CLR repo, let me copy this link and open it up here. So here's the repository in GitHub for the .NET Core. And if you were to look through this, it appears that there's one primary code base, but then there's a lot of optional code that's compiled for a specific target operating system and architecture. And I'm not a C++ or a C programmer. I'm merely looking at the names of files inside of the repository. And as you kind of dig through the subdirectories, like cross, for example, you can see the different architectures, whether it be ARM or ARM64, and so on. All right. So next up then, portions of the Core FX. Again, that's the class library of functionality that our applications rely on. They are platform specific, and other parts are, and most of it is platform independent, like we looked at because of this diagram here, right? So the majority is platform independent, but a couple of bits are platform specific. Again, things like system.io, for example. And so those libraries that have strong dependencies on the operating system, such as anything that works with the file system, the network, or low-level features like cryptography, are written with specific instructions for those platforms. But other things that are higher level, like link and collections and so on, they're written in C#, and therefore they're platform independent. Okay, so just want to give you a few key takeaways, and then I want you to read that article I told you about earlier. First of all, the Core CLR is the execution engine that hosts your application as it's running. It's responsible for providing life support, I guess you could say, to your application to keep it alive and healthy. And it provides a baseline implementation for things like data types and managing memory and more. And then there's the Core CLR, and it's platform-specific software that's built from one code base, but it's compiled into platform-specific instructions using conditional compilation to say, oh, we're going to compile it for a Linux distribution or a Mac OS distribution or a Windows distribution. Okay, well then do these different sorts of things, but it's all in one code base. And it's written using low-level programming languages like C and C++, since it needs to deal with the given operating systems. And then there are libraries that are defined in the Core FX that depend on sometimes depend on a specific version of an operating system and hardware architecture. That's platform specific. However, other higher level features of Core FX libraries are not dependent on a given platform, and they're typically written in C#. So don't forget, the next step, you need to go out and read or at least review this article. Again, that's the one by Matt Warren. And that's your homework assignment before you continue on to the next video. So we'll see you in that video. Thanks.